Hello everyone. So in this lecture I am going to introduce another class of methods for solving ordinary differential equation numerically. This particular class of methods is called Runge-Kutta method. So or in short RK method. So in the previous couple of lectures we have seen Euler's method. So in Euler method, in simple Euler method we were having the accuracy of order of h, while the modified Euler method we were having it of order h square. And we have seen in Euler method, if you want more accurate solution or a better approximation of the solution, what you need to do? You need to reduce the step size, that is you have to use smaller steps value of h. Or if we talk about Taylor method, if you want more accurate solution, what you need to do? You have to go for higher order terms. Higher order terms means higher order derivatives of a function, but whether you are decreasing your step size or you are calculating the higher order derivatives, in both the cases you need to do more calculation, computational complexity will increase. So in RK methods we attempt to obtain greater accuracy and at the same time avoid the need of calculation of higher derivatives or with a smaller step size. We do not want to reduce the step size. So how we can do it? We will evaluate the function f of x y at some selected points on each subintervals. Like in simple Euler method or Taylor method, we are calculating at initial point and last point. Here what we will do? We will take some selected points on the subinterval. So consider this. So first of all I will explain RK method of order 2 and then I will tell you how can we generalize it to in any order. So consider the initial value problem as dy over dx equals to f of x y with initial condition y at x equals to x naught equals to y naught. So for solving this problem using the Runge-Kutta method of order 2, first we need to define the modified Euler's method in the form y1 equals to y0 plus k, and here k will be half of k1 plus k2, where k1 is h times f of x naught y naught and k2 is h times f x naught plus h y0 plus k1, and this particular method is called RK method of order 2. So basically what we are doing? So RK method of order 2 can be given as, suppose I am having initial value problem as y dash equals to f of x y with an initial condition y x naught equals to y naught. So y1 can be obtained as y naught plus k, where k will be half of k1 plus k2 and this half of k1 will be h times f x naught y naught plus k2 will be h times f x naught plus h y naught plus k1. So what we need to do? First of all we need to calculate k1, then we need to calculate k2, we need to take the average of k1 and k2, that will be my k, and y0 can be updated as y1 equals to y naught plus k. So this is the overall algorithm for Runge-Kutta method of order 2. Now, graphically this method can be seen like this. I am having an initial point x, at this point I am having the value of the function y of x given by this particular point. I am having, and this is my function, this pink color curve exact function. I am taking the slope at this particular point x, which is given by this green line, and I want to find out the value of the function y at x plus h. So, what will happen? I will take the midpoint of this slope, that is somewhere x plus 0.5 h. So, midpoint of the interval. At this I will find out the point at the slope line. So, this particular point will be the y plus 0.5 k1. Now, at this particular point, that is x plus 0.5 h and y plus 0.5 k1, I will be having another solution curve given by this particular curve, that is y1x. Now, slope of this y1x at this particular point x plus 0.5 h will give me the value of function y at x plus h, that is y plus k2, and that will be the half of the Euler's step. You can see here, this is the difference in Euler step, and this is particularly y plus k2, that is Runge-Kutta method of order 2. So, in general RK method of order m can be written as follows, like in order 2 we are having two terms k1 and k2, like that in order m method we need to calculate k1, k2 up to km, and where k1 is given just like as in order 1 method, k2 will be just like at order 2 method, k3 will be h time f x0 plus alpha 2 h plus y0 plus beta 2 1 k1 plus beta 2 2 k2. Similarly, k4 can be given by this particular expression, and km will be finally with this one, where k will be the weighted sum of k1 k2 up to km, that is omega 1 k1 plus omega 2 k2 plus up to omega m km, where omega 1 omega 2 omega m are weights, that is between 0 to 1. And finally, once we will be having this k, I can write y1 equals to y0 plus k. The parameters alpha, beta and weights w are chosen to satisfy certain conditions. They are determined by expanding various functions in y1 equals to y0 plus k about x naught y naught, and comparing powers of h in the expansion of y x0 plus h. That can be seen, means in case of order 2 I will drive it, how we are getting these particular alpha, beta and w for a RK method of order 2. So, basically in RK method of order 2 I will be having k1 as h time f x naught y naught, k2 will be h time f x naught plus alpha h y naught plus beta 1 or simply beta k1, and then I am having omega 1 k1 plus omega 2 k2, this is equals to k, and finally y1 will be y naught plus k. So, this is the general scheme for RK method of order 2. So, y1 is y0 plus k, that I can write y0 plus omega 1 k1 plus omega 2 k2. So, y0 plus omega 1, the value of k1 I can substitute from here, h time f x naught y naught plus omega 2, the value of k2 I can substitute from here, h f time x naught plus alpha h y naught plus beta k, or this can be written as y naught plus omega 1 h f of x naught y naught plus, let us expand this term by the Taylor series expansion about x naught y naught. So, this will be omega 2 h into f x naught y naught plus alpha h f x plus beta k f y, that is the first order term. So, f x at x naught y naught, f y at x naught y naught, plus I will be having the second order term, that is will be h square by 2 into alpha square h square, the second order derivative of f with respect to x, that is the partial derivative, plus 2 alpha h beta k f y y, sorry, it will be k 1 because k we have taken here. So, k 1 and then k 1 plus beta square k 1 square f y y plus higher order term. So, this can be expanded like this. Finally, we can collect the coefficients y 0 plus h time omega 1 plus omega 2. So, I have taken this into f. So, please note that now I am writing f x naught y naught as f plus, so I have taken these terms, then I will be having this particular term h square. So, h into h square alpha into omega 2 into f x plus, as you can note down, this k 1 can be written as from this formula h of f. So, this term will be beta h f f y. So, h square I have taken out. So, it will be beta into omega 2 f into f y plus higher order term. This will be y 0 plus h omega 1 plus omega 2. As you know, for the initial value problem, y dash will be f of x y. So, this f I can replace with y dash plus h square terms. Now, the simple Taylor series expansion of y can be given as y 0 plus h time y dash plus h square upon 2 y double prime. Compare the various powers of h. From here omega 1 plus omega 2 will become 1. This is the first expression I am getting by comparing t power 1 of h, and then from the second what I am getting alpha equals to beta. Hence, I am getting, if I choose alpha equals to a, I can get beta equals to a because alpha equals to beta, and omega 2 will become 1 upon 2a, and omega 1 will become 1 minus 1 upon 2a. So, giving different values to a, in general we choose a greater than half or equals to half, such that we can generalize the various RK methods of order 2. For example, the classical method of order 2 can be obtained just by taking alpha equals to beta equals to 1. So, here a is taken as 1. So, omega 1 will become half, omega 2 will become half, and the corresponding this particular equation will become x naught plus h, y naught plus k 1, which is the standard Runge-Kutta method of order 2. So, let us take again an example and solve it using Runge-Kutta method of order 2. So, I am taking y dash equals to f of x y. So, here let us take f of x y as y. So, my differential equation is dy by dx equals to y together with initial condition as y 0 equals to 1. So, let us take h equals to 0.1, or let us find out more smaller value h equals to 0.1. So, y at 0.01 is given as y at 0 plus k, where k is half of k 1 plus k 2. So, k is half of k 1 plus k 2. So, let us calculate k 1 for this particular example. So, k 1 will be h times f x naught y naught. So, h is 0.01 into f of x naught y naught will be y naught, which is 1. Similarly, I can calculate k 2. K 2 will be h time f x naught plus y naught, sorry, h time f x naught plus h y naught plus k 1. So, it will be 0.01 into, so this will become y naught plus k 1, y naught is 1, k 1 is 0.01. So, 1.01. So, it will become 0.0101. Now, k will become half of 0.01 plus 0.0101. This is half of 0.0201, and it will be 0.010050. Hence, y at 0.01 can be given as 1.01005. And so, value from this table at x equals to 0.02, y will come out 1.020201, at 0.03 y will come out 1.03050454, at 0.04 it will be 1.040810. The exact solution of this particular differential equation is y equals to e raised to power x, that can be obtained just separating the variables of y and x in different sides and then integrating, and exact solution at y of y at x equals to 0.04 is given by 1.0408, which is same as we are getting using the Runge-Kutta method of order 2 for this particular example. Then if we talk about error in this particular method RK method of order 2, then the truncation error will be obtained as r equals to yx1 minus y1, and that will be the term which we have left out for third order of h cube. So, hence error will be accuracy will be order of h cube. So, local discretization error of this method is of order h cube, whereas the Eilers and quadratic Taylor methods were having order of h square. So, therefore, we can expect to be able to use a larger step size in this method when compared to the Eilers method. The price we pay for this is what we must evaluate the function fxy twice, that is one for k1, another one for k2. This method is also known as Euler-Cauchy method. Third order RK method can also be constructed by taking k1, k2, k3 and carrying out the same analysis as we have done for order 2. Here we are talking the RK method of order 4. So, in its simple form, a fourth order RK method may be expressed as, so there we will be having 4 terms k1, k2, k3, k4. K1 is given as h times f x naught y naught. Then we will make use of this k1 for calculating k2. So, k2 will become h times f x naught plus alpha 1 h y naught plus beta 1 k1. K3 will be h times f x naught plus alpha 2 h plus into y comma y2 y naught plus beta 2 k2. And finally, k4 will be h times f of x naught plus alpha 3 h comma y naught plus beta 3 k3, where k is omega 1 k1 plus omega 2 k2 plus omega 3 k3 plus omega 4 k4, and finally y1 can be obtained just like in the method of order 2, that is y naught plus k. Basically, we are having 10 unknowns and procedure for computing their values is same as we have discussed in order 2 method. However, we will be having less number of equations than the unknown. Therefore, we have freedom to assign arbitrary values to some of the unknowns, and in this way we will get a class of RK method of order 4. The most classical method which we take is something like this. We take alpha 1 as 1 by 2, beta 1 as 1 by 2, then alpha 2 as 1 by 2, beta 2 as 1 by 2, and finally alpha 3 beta 3 as 1 and 1, and we take the weighted average as omega 1 as omega 1 k1. So, 1 by 6, omega 2 as 1 by 3, omega 3 as 1 by 3, and omega 4 as 1 by 6. So, scheme will become like this. Let us take an example, and as we have seen in the method order 2 method, the truncation error is of order h cube. So, here error will become of order h5, h raised to power 5, 1 less than the polynomial degree of the polynomial which we are taking. So, compute y at x equals to 0.2 and 0.4 by fourth order Runge-Kutta method for the differential equation dy by dx equals to y minus x, where y at x equals to 0 is given by 1.5. So, first of all we will take h as 0.2, x 0 is 0, y 0 is 1.5. So, k1 will become h times f x naught y naught. So, it will be 0.2 into 1.5 minus 0, so 0.3. The k2 will come out as 0.310, k3 will come out as 0.3110, and finally k bar will be 0.322. By taking the weighted average of k1, k2, k3 and k4, I will calculate k, and k will be my 1 by 6, 0.3 plus 2 times 0.31 plus 2 times 0.3110 plus 0.3222, and it is coming out as 0.3107. So, finally, y1, that is the value of y at x equals to 0.2 will be y naught plus k, and it will be 1.5 plus 0.3107 that is 1.8107. Similarly, taking the initial values at x1 0.2 and y1 as 0.8107, I will calculate the value of y at x2, that is 0.4, that is basically y2. So, similarly for this I will calculate k1, k2, k3, k4. So, these are the this is the value for k1, the value for k2, value for k3, value for k4. Finally, weighted average will give the k, which will be 0.33517. So, y2 will come out finally y1 plus k, and it is 2.1459. So, in this way I can implement the Runge-Kutta method of order 4, which is having the accuracy of order h raised to power 5. I can generalize the Runge-Kutta method of order 3 also, which will be having accuracy of h raised to power 4. So, in this lecture what we have learned? We have learned another class of numerical methods, that is Runge-Kutta methods, and we have done the method of order 2 in detail. For this we have done the derivation, we have done the error analysis, we have also seen the RK method of order 4 in detail, we have taken an example, we have found the value of y at 2 points, that is x equals to 0.2 and 0.4 if the value of x at 0 value of y at x equals to 0 is given. So, all these methods starting from the Euler's, then Taylor, then RK methods, what we are doing for calculating the value of y at x equals to x1, we are using only the value of x at x0. So, what we are doing? We are taking a single step. For finding the value at next point, we are using the value of current point. So, all these methods are single step. In the next lecture, we will see another method which is different from these methods, because that particular method will use multi steps. So, for finding the value of y at x equals to x1, it will take use the value of x at x0 and at some previous points, and based on those points it will fit a polynomial, and for the next point it will extrapolate the value of the function for the next point. So, thank you very much.